In this tutorial, we are going to talk about the other method of demodulators, which is the envelope detector. And as I said in some of my videos, I said that I normally refer envelope detector as the switching method of demodulation because it also makes use of diode, as we did for modulation. So for the switching method, for the envelope detector, the same principles apply here, of which we have our diode, and then we have our S of T, which is our modulated signal. After passing it through the diode, we get the output results, and then we pass the output result through a low pass filter. And then from there, we get our message signal. So this is another method of demodulating a modulated signal. So as I said earlier on, envelope detector, it's used to detect a higher level amplitude modulated wave, right? So as I said earlier on, when we were doing the modulation, we said the modulator is the diode at the end time. And now, since we are passing the modulated signal through the diode now, the demodulator is also our diode. Therefore, we can replace the envelope as diode detector. Aside that, when you look at the original circuit, which is, for instance, let's do this. This is the diode. It's being coupled with a parallel capacitor and a resistor, which is being arranged in parallel. This is what the low pass filter contains. And it works in the principle that during the forward bias, of which S of T is greater than the voltage across the capacitor, there will be a forward bias. And therefore, this modulated AM wave will be charging this capacitor. So at the point where the capacitor voltage becomes greater than the S of T, this diode will be in the reverse bias, and therefore this capacitor will be discharging through the load, which is the resistor. So basically, in simple terms, I will say that in the positive half cycle, the diode will conduct and charge the capacitor up to the maximum level or the peak level. And at the point where the value of the amplitude modulated wave becomes less than the value, the diode will be reverse biased. That is, if this S of T becomes less than the voltage across the capacitor here, there will be a higher potential here and there will be a lower potential here. And therefore, this diode becomes reverse biased. And therefore, this capacitor will start discharging through this resistor till the next half cycle of this AM wave comes in. When it happens that way, it will get to a point whereby the voltage across this one becomes also greater than the voltage across the capacitor, and then the diode comes in forward bias and it will start conducting. So this process will repeat itself in a number of times, and therefore it's being advised that when you are selecting the components for such applications, you must do it in such a way that the capacitor will charge quickly. That is, it will have a lower time constant. It will have a lower time constant. If something have a lower time constant, let's say 2, and someone has a lower time constant, which is maybe 5, this one will disintegrate quickly than that of the one having a lower time constant of 5 seconds. Therefore, you must select the component in such a way that you have your capacitor to discharge quickly, or let's say the capacitor to charge quickly. That is, it must have a lower time constant in terms of charging. It must reach its maximum level within a shortest possible time, but it will have a very long discharging time. That's the time that is being discharged through the load, which is the resistor. It must have a very low discharging time, which is the discharging time constant. That means that it must have a very large time constant. In this case, we will get the capacitor voltage waveform to be the same as that of the diodes, the diode of the AM wave that we are trying to demodulate, and therefore it will make the AM waveform of the diode or the envelope will be almost similar to that of the modulating signal, which is the message signal that we are looking for. But not to waste much time, we will try to do some mathematical analysis for the switching modulator or the envelope detector. For the same principle as we did for the switching modulator, we assume that this capacitor, this diode, it's our demodulator, and mostly or always it's being multiplied by a train of pulse, which is G of t. And in my previous tutorial, I show you how the train of pulse look like. I'm saying that the train of pulse looks like this, and then we have to find its Fourier series for this. That's the train of pulse. Therefore, the Fourier series for the train of pulse is equal to this train of pulse, this square wave train of pulse is more like a duty cycle, as I said earlier on. It's being used to control the switching time, the switching of the diode. Therefore, my G of t is equal to 1 of 2 plus 2 over pi cos omega ct. I've already explained this, and if you want the full proof of how this one came in by using the Fourier series, you can refer to your signal and systems class. So now, the same principle applies. This is my diode. The input, my output. When it is conducting, the relationship, let's say here is V1, here is V2. When it is conducting, the relationship between the output signal and the input signal, it's equal to V2 equal to V1 multiplied by G of t. So this is the relationship that exists between the output and the input signal of the diode when the diode is in forward bias. So now let's come out with our V1. We all agree that we are saying that the input of our diode is S of t. Therefore, our V1 is going to be S of t, which is also equal to AC into bracket 1 plus Km of t cos omega ct. Let's do the simplification here. So we can see we have our AC plus our AC Km of t cos omega ct. Therefore, we can see that our V2, which is the output of the diode, is going to be our AC cos omega ct plus our AC Km of t cos omega ct. Then multiply by G of t, of which the G of t, by using the Fourier series, we are going to get 1 over 2 plus 2 over pi cos omega ct. So this is what we have. The rest is simplification. So AC cos omega ct times 1 over 2, we are going to get 1 over 2 AC cos omega ct. Also, AC cos omega ct times 2 over pi cos omega ct, we are going to get plus AC or 2AC over pi cos squared omega ct. That is, this one was used to multiply this. Now let's take the second one. AC Km of t multiplied by 2, we are going to get plus 1 over 2 AC Km of t cos omega ct, then plus this same thing multiplied by 2, we are going to get 2 over pi AC Km of t, 2 over pi AC Km of t cos, because now this one it's a cos, and multiplied by, we are going to get cos squared. omega CT. Now this is the output of the diode. When we get this, what is left is to pass the resultant one into a low pass filter. This is a V2 LPF. And as I explained earlier on, we are passing it through the low pass filter because we want our message signal, and we all agree that the carrier signal has a higher frequency and the message signal has a lower frequency. So when we pass through a low pass filter, it will allow the signals with the lower frequencies to pass whilst blocking the signal with the higher frequencies. So in looking at this one, you can see that this one contains only the omega C, which is the carrier frequency, which is a higher frequency. Therefore, the low pass filter will block it. Looking at the second one, the function, cost function square has been squared. That means even the frequency of the carrier signal has been squared. We don't even have the message signal inside, and therefore that one also goes to 0 because the low pass filter will not allow it to enter. Let's look at the next one. The next one is this one. This one contains our message signal M of t, and it also contains the omega angular frequency of the carrier signal, which is a higher frequency. And therefore, this one will also be attenuated because the low pass filter will block it. Let's look at the last one. This last one is 2 over pi AC k M of t cos squared omega ct. Someone will say that it will be cancelled out because it contains the frequency of the carrier. But remember that this one can be simplified for us to get a constant and the other parts by using trigonometric identities. We didn't do for this one because the low frequency signal, which is the message signal that we are interested in extracting, is not part. So we didn't do any simplification using trigonometric identities for it. And therefore, at the end of the day, we are going to get our output, let's say V out of the signal, to be 2 over pi AC k M of t cos squared omega ct, which is the V out. When you get it like this, we can use the trigonometric ratios or identity to help us get the constants and the other counterparts. And how do we do that? Remember that drawing either the derivation of the square law demodulator, we came out to the fact that cos square theta equal to 1 plus cos 2 theta over 2. So with this, our theta being omega ct, we are going to have our V out to be equal to 2 over pi AC k M of t being multiplied by 1 over 2 plus 1 over 2 cos 2 omega ct. You can see also that the angular frequency of the carrier signal as the other part of the equation has been doubled, and therefore the frequency has even increased. So this part, when we pass through a low pass filter again, this one will go to 0. Therefore, we are left with this 1 over 2 multiplied by this. So the final equation, which is our M of t, or let's say our V out, is going to be 1 over 2 multiplied by 2 over pi. 2 over pi, okay, let me write here. The final equation is going to be 0 equal to 1 over 2. Let's say these two will cancel these two, so it's 1 over pi multiplied by AC km of what? T. So this is basically the output f over ACK over pi. This is our message signal. And as I was saying, or doing the explanation for the envelope detector, I was saying that there will be some scaled version. There will be some scaled version. And therefore, you can pass it through a low pass filter again to kind of remove that DC component. This is a DC component, this one. Or After passing it through the diode and then passing it through the low pass filter, you pass it through a multiplier, and that multiplier will have a gain of pi over AC in order to get your desired output m of t. When you do that, we are going to get k m of t, and remember that the k here is our amplitude deviation. So in summary, I will say that when you want to use the envelope detector method in demodulating an modulated AM signal, you pass the modulated AM signal through a diode, represented it mathematically. It will multiply it by, the diode will multiply it by a train of pulse, and I showed that train of pulse, it's this one. So when we are done with this, the resulting output, because of the nonlinear nature of the diode, some harmonics will be introduced into the system or the resulting output. And therefore, when we pass it through the low pass filter, it will attenuate all the unwanted frequencies, leaving the lower frequency, this is our message or the desired frequency signal, to pass. At the end of everything, there will be some scale version of division. And in order to remove that scale version of division, you have to pass the resulting output of the low pass filter through the multiplier with a gain of the pi over AC. And that will eliminate it, giving us k m of t, which is our message signal, where our k is the amplitude deviation. So this is where I'll bring the envelope detector demodulator to an end. And in my next tutorial, we will be talking about the various types of AM modulation. So thank you for watching, and see you in my next video.